8.3 is called logarithmic functions and integration, but what I am going to actually say is it's the integration of any type of composition function to the negative 1. So for example, if I wanted to integrate something like this, 1 over x, and it was with respect to x, so I'm trying to integrate it, what we don't have is any kind of rule that we can integrate a quotient. So what I would do is I would rewrite this as x to the negative 1 dx. Now here's the problem. Our integration process would say something like this, that I would add 1 to my exponent and then divide by the result of whatever I had. So divide by negative 1 plus 1. So this would lead to me saying, alright, it would be x to the 0 over 0, and I would get some sort of undefined. So here is our issue. Here's another example problem of this same type of issue. If I were to have x over x squared plus 1, and I was integrating with respect to dx. So once again, we could try to say, well, let's try to rewrite this integral. So I would rewrite this as x times x squared plus 1 to the negative 1. Just because I was trying to avoid the fact that here I have what's going on is a quotient, and I don't have any integration quotient rules. So what I would be left with is something like this. So now once again I would be saying, alright, this is a composition function, x squared plus 1 to the negative 1. So I would let u equal x squared plus 1. I would go ahead and hope for, with integration, that with this u substitution I could achieve some sort of du dx relation to get rid of this. So I'm going to rewrite this as du dx. I'm going to derive that u function that I've identified as 2x. Alright, and then I'm going to multiply both sides by dx. Alright, so here's the thing. I almost have an x dx in my equation that I could sub in this du, except for the fact that I have this 2 there. So I would multiply by 1/2 on both sides, or in other words, divide by 2. So here I have it. I have 1/2 du is equal to x dx. This is my x dx that I would replace with a 1/2 du. Okay, and then I have this u, which is equal to x squared plus 1, u to the negative 1, and now this is what I'm trying to integrate. Once again, we have this issue of the negative 1, because if I pull out that 1/2, I still have u to the negative 1 du, and once I try to integrate this, I'm going to get that issue of dividing by 0 again. So you get this undefined. So how do we approach something when we're trying to integrate any type of composition function to the negative 1, and you're doing u substitution, or you're moving along and you get to that point where you try to integrate and that exponent of negative 1 is just holding you back? This is what we're going to be focusing on. Recall that we have a rule that stated that the derivative of the natural log of x is equal to 1 over x. Recall that we also had, if you were trying to derive the natural log of some sort of function with respect to x, you would just have to simply do 1 over u times du dx, which also du dx, the derivative of u with respect to x, could be notated like this. So this was something that we would oftentimes use as well. So what this leads to is the backward rules. Here were our differentiation rules for the natural log, and so now if we were ever trying to integrate any one of these types of results, so this is a function that's a derivative. Here's a derivative. It's the derivative of the natural log of x. So if I was trying to anti-derive something like 1 over x, what we're going to be getting is the natural log of x. So here is what we would have. So here are more properties. I actually should write rules. These are more rules. These are the ones that you should write on the top of your paper in this section, because you're going to be dealing an awful lot with these. I'm going to start us off light, and I'm going to do number 1. Alright, so I'm going to start us off with number 1, and what they ask us to do is integrate the function 3 over x dx. So they're trying to make us work backwards with this. Basically, what I could write is 3 times x to the negative 1 dx. Okay, so this is a scalar multiple, so I can pull it out. and what I have is x to the negative 1 dx. So here is where you would have that issue of integration, and you would get yourself an undefined. So if you can recognize it straight off the bat as 1 over x dx, and this piece right here is using that rule, and I'll scroll up real quick. This rule right here, so we're going to be taking the natural log of the absolute value of x plus c. So this is going to be 3 times the natural log the absolute value of x plus c. Because this is an indefinite integral, there is no bounds, we need that c. Alright, let's go to something a little bit more complex. I'm going to do number 9 is asking us to integrate this function. Alright, once again I have this issue that I don't have quotients to integrate or any kind of rule. So what I am going to do is I'm going to take this x and divide it by everything on top. So this is just going to be equal to, if I take x squared divided by x, I get x. Minus, if I take 4 divided by x, I get 4 over x, because that doesn't simplify at all, and I have integrating with respect to x. So now on this side, as I'm integrating with respect to x here, we do have a rule, a sum and difference rule, that I can individually integrate. Okay, I also have a rule that I can pull this scalar out. So I have x dx minus 4 times the integral of 1 over x dx. And this is what should pop out at us. Whoops. So right here, this is a typical old-fashioned, we have an x to the first, so I'm going to add 1 to my exponent and divide. So I have 1/2 x squared minus 4 times the natural log of the absolute value of x plus c, because it is going to be indefinite. I'm going to do number 6. Sorry, I'm kind of backtracking. So here we're going to do number 6. They ask us to integrate 1 over 3x plus 2 with respect to x. Alright, so here we don't directly have an integral of 1 over x, so that's not a problem. What I'm going to say is this is a function within that function of 1 over x. So instead I'm going to let this be our u. So we're going to say u is equal to 3x plus 2, and if I were to derive that, that's just going to be equal to 3. So we have du dx is equal to 3 if you go through and derive this. So what I am looking for is, this is going to be leading me to du is equal to 3 times dx, and what I hope to achieve is to replace all of this with u's. So I'm going to replace my 3x plus 2 with this u. However, I did what it looks like is I want a 3dx in my equation that I could sub in du for it. But since I don't have that, I am going to multiply this by 1/3 and multiply this by 1/3, thus canceling this out. So we get 1/3 du is equal to dx. So I do have this dx in here, and this is the hardest part for a lot of you. I have this dx is equal to this right here. So in goes this for the dx. I'm going to get the integral of 1 over u times 1/3 du. And here is the scalar that has been created in this process, but that's okay. I'm just going to pull that out, because when integrating, if you ever have a scalar multiple, you can just pull it out to the front and multiply it back in later. So this right here should pop out at you, because once again, up to our rule, this is saying that if you're ever integrating with respect to u, and then you have a 1 over u, it's just the natural log of u plus c. Whoops. So in this case, I'm going to have 1/3 times the natural log of u, which I am going to I'm just going to write it, and then plus c, but then don't forget you need to resub in, because we were integrating with respect to x. So 3x plus 2 plus c. Alright, for numbers 13 and 17. I am going to tell you you're going to need long division of polynomials. Okay, this is not something that I'm going to go over in this particular video. I might make a video on long division here in a second. I might make a video of long division of polynomials if we are struggling with it, but this is something that you can look over in example 5 on page 530. So once again, if you're struggling, please go there and look over that example. Otherwise, I may be making a video on that. We have one more type of problem that we're going to be looking at, and that's problem set starting at 33. So you have one more rule in this section that's stating this: if you're ever trying to take an exponential, base a, base any number besides e, and we're trying to integrate, what it's going to look like is this formula right here, or this rule right here. So this is just one more rule that we're using. So I am looking at 30, I'm actually going to do 35 here. Looking at 35, what we have is 2, -1, 2x dx. So I'm going to just, once again, it's strictly using rules at this point. I'm going to be looking at my base. It isn't 2. So it's going to be equal to 1 over the natural log of 2 times 2 to the x plus, actually, sorry, in this case we don't need that plus c. And since this is a definite integral, what we are going to actually have to do is calculate this. So I'm going to plug in 2. I'm going to do big F of 2 minus big F of -1. Because oftentimes what they do, this is an antiderivative equation right here. We have integrated, and the process of integration gets us an antiderivative equation. And so what we often label an antiderivative is a big F of x. And so since we're specifically plugging in 2 and -1, that's what it's going to look like. So we have 1 over the natural log of 2 times 2 to the 2 minus, and then we have 1 over the natural log of 2, and then times 2 to the -1. So what I'm going to be getting something is 4 over the natural log of 2 minus, this right here is actually going to bring that 2 down to the bottom. So we have 1 over 2 times the natural log of 2. Okay, if you wanted to condense this, you would need to get a 2 up here times a 2 up, 2 on the bottom, 2 on the top. You're going to get 8 minus 1, which is 7 over 2 natural log of 2. Okay, and then you could get a rounded answer, but I think that's good enough for me.